Okay, so today we are going to talk about induction. Okay, mathematical induction. So this is one of the most fundamental proof techniques there is. It's the one that we are going to use most often. Now, induction is particularly well tied to computation in the following sense. So first of all, induction is intimately tied to recursion. So recursive algorithms. Whenever you analyze a recursive algorithm, you do that by induction. Another thing that happens is when you're trying to analyze programs, you're analyzing a loop, you always analyze it using, again, induction. So this is going to be an extremely fundamental technique which you'll use whenever you're analyzing algorithms or programs. Okay, so what's induction? I hope that most of you have already seen this in an elementary form in high school, but we're going to learn this at a deeper level here. Okay, so let's start from a simple example which many of you have probably seen. For all n in the natural numbers, summation I equal to 0 to n of I is equal to n times n plus 1 over 2. Okay, so let's just see what this is saying. For n equal to 0, so when n equal to 0, you're summing from 0 to 0. So you just get 0. 0 times 1 over 2. That checks out. N equal to 1. 0 plus 1. 1 times 2 over 2. N equal to 2. 0 plus 1 plus 2. 2 times 3 over 2, which is 3. Right, and you can sort of work your way through and you can check. Seems to work. Right? Okay, but now, no matter how many such examples you work through, you won't have proved this statement. So how do you actually prove this statement? Well, the strategy in induction, one way to think about it is to observe that in this particular case, if you work your way through a particular example, if you work your way through an example n equal to k, so if you work your way through the example n equal to k, and you show, yes, it does work there. Now, you don't have to work from scratch to figure out that it works for k plus 1. So now if you want to do the example k plus 1, you can sort of bootstrap off of k. And some of the calculations you've done, they're already useful to do the calculation for k plus 1. So all you have to do is to check that if this example worked out, right, then in fact, why is it that the next one will also work out? And in fact, you can automate that process. And you can say, actually, if it worked out for k, it'll always work out for k plus 1. Right? We'll just go ahead and do that extra calculation. That extra calculation is simple. It's a tiny, simple calculation. And we'll do that in full generality. And so once we have done that extra calculation in full generality, then we sort of say, okay, well, now it's as though we've worked out infinitely many cases. Right? So let's just do this. So let's say we worked it out for k. So we verified that summation I equal to 0 to k of I is k times k plus 1 over 2. So we checked this out. This we verified. Okay? So now, let's see what's the extra calculation we have to do for k plus 1. So for k plus 1, what we do is we need to evaluate summation I equal to 0 to k plus 1 of I. Okay? But what is this? Well, this is summation I equal to 0 to k of I plus k plus 1. Yeah? But remember, we already checked that this is, that the statement is true for up to k. Right? So we know that this value is equal to, by the fact that we've checked it out, this is equal to k times k plus 1 over 2. And so now we can just simplify. This is equal to k plus 1, which we get in common, times k over 2 plus 1, right? Which is k plus 1 times k plus 2 over 2, which is exactly what we wanted to show, right? Because when we are going up to k plus 1, it should be k plus 1 times k plus 2 over 2. So what we've done is we've actually given a general procedure. We've said, look, if you checked your examples up to k, then with a small extra calculation, we can check that in fact it'll also work for k plus 1. But since k was completely general, what this gives us the right to do is to say, well, look, we checked that it works for 0, and now we also check that whenever it works for k, it works for k plus 1. And so it works for 0, it works for 1, it works for 2, it works for 3, and so on, and we don't ever have to stop. So we've proved it works for all n. Okay, that's induction. Is this clear? Right? So we are trying to work through all possible examples. We don't have the time to do it. So we do something general. We say, look, if we work through a particular example, because of the structure of the problem, going from here to the next example is not that hard. So we just show, well, if we got this far, we can get to the next step. And now since we showed this in full generality, we've shown it for all n. Okay? Okay, so now a proof by induction is just a way of folding this into a formal argument. There's a format in which we do it, but this is the idea. Right? So if you remember the idea, that's the main thing, and then we'll always say it in a certain format. Okay? Okay, so how do we say this argument in this format? So what we do is we say, well, we are going to do a proof by induction. Okay, so it's a proof by induction on what? On k. Induction on n, I guess. Okay. Proof by induction on n. That's what we are doing in induction on. So we start with what we call the base case. We say it holds to begin with, for n equal to 0. So we check that it works for n equal to 0. Well, we checked up there, so that's good. Right? So you go through and check that the statement is actually correct when n equal to 0. Okay, so then what do you do? Then you say induction hypothesis. Suppose that we know that for some k, we've already established this statement. So say we have established that summation I equal to 0 to k of I is k times k plus 1 over 2. This is a hypothesis. This is something that we get to assume. Okay? We assume that we've shown this already. Right? We don't have to show it. Okay, so this is what we're going to assume holds. We assume that this is true. And then we do what's called the induction step. In the induction step, we want to prove the statement for k plus 1. Okay? So we want to show summation I equal to 0 to k plus 1 phi is k plus 1 times k plus 2 over 2. In order to do this, we are allowed to assume this statement, right? And anything else that's true. But in particular, we are allowed to assume this particular statement. Okay, and so what does the induction step look like? Well, it looks exactly like that, right? So we say this thing equal to summation I equal to 0 to k of I plus k plus 1, which is equal to dot dot dot, which is equal to dot dot dot, which is equal to k plus 1 times k plus 2 over 2. Okay. So we've successfully carried out our induction step, and that's the end of the proof. Okay? That's the proof by induction that summation I equal to 0 to n, I is n times n plus 1 over 2. Is everyone clear about this? Okay. So let's look at the general form of induction. So in induction, we're proving a statement for all n and n, some statement p of n. Okay? The proof by induction goes like this. Base case p of 0. You check that p of 0 holds. Induction hypothesis. Assume p of k. Induction step. Show that p of k plus 1 holds. Right? In other words, once you assume p of k, show that p of k plus 1 holds. Right? In the induction step, you're really showing p of k implies p of k plus 1. Here's a way you can picture it. You can picture it as a bunch of dominoes that you line up. There's p of 0, p of 1, p of k plus 1. Okay? What you're trying to do is you're trying to show that these propositions are like dominoes. They've been set up so that as soon as you tip one over, the next one tips over too. That's your induction step. Right? The induction step says you lined up the dominoes so that when the previous one goes, the next one goes. Right? The base case, what does that say? You give it the initial push. Right? Until you push the first one down, nothing happens. So you need the base case, you need to line up your dominoes, and then it all goes. Okay, so let's do another one. N cubed plus 2n is always divisible by 3. Okay. So proof by induction, base case, n equal to 0. That's trivial, right? Because everything divides 0. Induction hypothesis, So assume that 3 divides k cubed plus 3k plus 2k. And now induction step. We want to show 3 divides k plus 1 cubed plus 2 times k plus 1. Okay? So we want to say k plus 1 cubed plus 2 times k plus 1 is a multiple of 3. So let's write it out. So we want k plus 1 whole cubed plus 2 times k plus 1. Everyone remember how to expand k plus 1 cubed? Yeah, well, remember a plus b. Well, let's start with something we remember, right? It's a plus b squared is that, right? What's a plus b cubed? So it's a cubed plus 3a squared b plus 3ab squared plus b cubed. So this is k cubed plus 3k squared plus 3k plus 1 plus 2k plus 2. Okay. Which is now, what do we want to do here? We want to show 3 divides this. Okay, so we have a mess here, right? I mean, what are we going to do with this? So how do we want to clean this mess up? Well, remember, there are 2 things we can count on. Things we already know are divisible by 3, and things we know are divisible by 3 because of the induction hypothesis. So let's pick out the induction hypothesis here. So there's that, and there's that, right? K cubed plus 2k. So let's k cubed plus 2k. And then let's bunch all the rest of the stuff together. So that's this and that. Plus 3k cubed plus 3k squared. No, sorry, it's 3k squared plus 3k plus 3. 2 plus 1. Okay, so this is divisible by 3 because of the hypothesis. This is divisible by 3 just by looking at it. It's divisible by 3. It's 3 times k squared plus k plus 1. And so the sum of them is divisible by 3. Right? The whole thing is divisible by 3. Yeah? Is everyone happy with that? Is that too fast? This is divisible by 3. It's of the form 3 times a. This is of the form 3 times b. So it's of the form 3 times a plus b. So it's divisible by 3. So we are done. So that's the end of the proof by induction. By the way, let me tell you something. So, you know, these may not be the simplest proofs there are of each of these statements. There might be other ways of doing this. For example, on this particular, the first statement that we proved here, there's a story about this. The person who is considered by many to be one of the greatest, so the person who is considered to be one of the greatest mathematicians of all time, but by many is considered to be the greatest mathematician of all time is Gauss, Carl Friedrich Gauss, from about 250 years ago. So there's a story about him. He was sort of a child prodigy. He was so in primary school, he was being punished in class, and so the teacher asked him to count from 1 to 100. You know, just not count, but add up the numbers from 1 to 100. Thinking that would keep him occupied for, a good period of time. And instead, almost instantly, within seconds, he said 50-50, 50-50. Right? He was solving this problem, and he worked out in his head, it's n times n plus 1 over 2. Well, not quite, but implicitly he worked out it's n times n plus 1 over 2. So how do you think he did that? See, here's what he was doing. He was saying, well, he had to add 1 plus 2 plus 3 plus ... plus 98 plus 99 plus 100. Okay? This is what he was trying to do. And so in his mind, he put these together. He said, well, 1 and 100 is 101. 2 and 99 is 101. 3 and 98 is 101. How many of these do I have? 50 of them. So it's 50 times 101. This he could do in his head. So he said, well, the answer is 5050. Okay? But this is exactly what's going on there. Right? It's if you had 1 plus ... plus n, well, how many times do you have n plus 1? You have n plus 1, n over 2 times. Right? That's the formula. Right? So the thing that you should remember is proofs are ways of sort of verifying that something is correct. It's proving something is correct. But beyond that, there's a way you imagine things. You know, it's not all there is to it, right? You know, you look at these things and then there has to be a picture. Sometimes you think about it in pictures, this way or some other way, right? Okay? So there's a lot that goes on behind the scenes of a proof. Okay. Now let's do another example of induction, but this one's going to be a slightly more non-trivial example of induction. Okay? So for this, we'll go back to sort of this problem of map coloring. So what's map coloring? So you're given a map of some region. You know, who knows? You know, it's divided up into states or whatever it is, and you want to make a nice map so that you don't get these regions confused with each other. So you color these regions with different colors, but you don't want to assign a different color to each. You know, you don't want as many colors as the number of regions. You want to use, you know, some small number of colors. So you might make this blue and green and yellow. This one can be. Sorry. You know, if they meet at a point, that's okay. You know, it's okay if green and yellow meet at a point, but you don't want them to share any lines in common. You know, you don't want them to share a border in common. So, for example, this one can be blue again, and this one could be green. You know, and so you can sort of reuse colors as you go along. Right? So you might use yellow here, blue here, etc. And so there was this question, well, if you were trying to make a map in the most devious way, what's the maximum number of colors you could force the map maker to use? Right? You know, what's the most unfortunate map there could be in terms of sort of in terms of forcing the largest number of colors to be used? And people tried, and they could. It's easy to get 4, but nobody could come up with any map where you could do more than 4. Okay, and there was actually a conjecture from about the 1850s, which is called the 4-color. Well, I don't know if it was already called the 4-color theorem or the conjecture, but you know, this goes back to the 1850s as a conjecture, but it wasn't proved until 1976. So it took over 125 years to actually prove the theorem. But what's very interesting is when it was finally proved, so before it was proved, there were many proofs that were announced, and every time a proof was announced, there was a flaw in it. Somebody found that there was a problem with the proof. Okay, something didn't quite work. But this one, there wasn't a flaw in. But it still caused people to be extremely uncomfortable. Because it wasn't a proof like this. You know, it eventually the two mathematicians who proved it, they were able to reduce to a number of cases. But the number of cases was something like 2,000. And then they used a computer to check. Okay? And this made mathematicians extremely uncomfortable. Because finally now proofs and programs were coming together in this way. Okay? So this was sort of a landmark proof in the history of mathematical proofs. Okay, so we are not going to prove this. But what we are going to do in this lecture is we are going to prove the two-color theorem. So in the two-color theorem, we have maps of a particular kind. So let's say this is our map. And now we have lines that divide the map into regions, but the lines go either from one end to the other, like that, or they might go like that, or they might even go like that. Right? So every curve that I've drawn is closed. Either it's closed or it goes from the edge to edge. Right? It doesn't stop in the middle. Okay? So now I've divided up this plane into regions, and the claim is I can always color it using two colors. So if I color this red, blue, then this has to be blue, this has to be red, this has to be blue, and look, you know, this last one behaves itself. So it's forced to be red from this side, and would be a disaster if it was forced to be blue from that side. But no, it's forced to be red from both sides. So you can go ahead and fill it in. And similarly, well, okay, so what about this one? Well, it's forced to be blue, and now this one, it's consistent. It can be red, that can be blue, that's got to be red, and then look, it all worked out. These two worked out to be fine, and this could be blue, and that one, you know, fits in nicely, and there's a blue here which doesn't contradict any. Okay, so it all worked out. So how did we know it would all work out? How would we prove that you can always, no matter how you draw these lines, no matter how many you draw, you can always color with two colors? Okay. So let's go ahead and prove this by induction. Okay, so let's go ahead and prove this by induction. So base case. So, sorry, induction on what? What are we going to do an induction on? On n. Right? Isn't that what we should do in induction on? No? Yeah, what's n? What do you want n to be? Yeah.
Number of lines.
Oh yeah, number of lines. It's the number of lines. Okay? So base case. So what should the base case be? N equal to 0. Okay, n equal to 0. Does it hold? Yeah, sure. Okay. That's trivial. What's our induction hypothesis? holds with k lines. Right? So if you have any map with k lines of this kind, you can color it using two colors. Step. Okay. So what's the step? Now we have to show that if you're given an arbitrary map with k plus 1 lines, then we can two-color it. Color it with two colors. So we start with an arbitrary map with k plus 1 lines, and we want to show it's all going to work out. We want to show two coloring. We want to color it using two colors. Okay. So how are we going to do this? Well, here's a map. Let's say with k equal to 3, so we have 4 lines. And now what do we do? How are we going to show that we can always color this with two colors, no matter what? Well, look, we have to use the induction hypothesis somewhere, right? So what do? Well, we go ahead. So we start with our k plus 1 lines. We temporarily delete one line. Okay, so we go ahead and temporarily delete this line. So now we have a map with k lines. Induction hypothesis, we can two-color it. So now we apply the hypothesis. We can two-color it. Okay, so let's two-color it. There was red, blue, red, blue, red, blue. Okay? Okay, so far so good. So now we go ahead and put this line back. And now what do? Now it's no longer a good coloring. So what do? Yes? Very good. So what you do is you take all the colors on one side of the line, say the inside, and you flip them. Right? If it's blue, make it red. If it's red, make it blue. The claim is now you get a valid coloring. So, in other words, right now, this region, this blue region, got divided into two. There's blue inside and blue outside. Right? So each of these regions became blue inside, blue outside. This was red inside, red outside. Blue inside and out, red inside and out. Right? That's what the coloring looks like right now. What you do is take everything on the inside and you flip it. So you replace this by red, replace this by blue, replace this by blue, red, red, blue. Okay? And the claim is this is a valid coloring. Okay? For it to be valid, what does it mean it's a valid coloring? It's got to be every color is blue or red. Secondly, whenever you look at a line and you look at the region on the two sides, they're different. Okay. So why are the regions always different on two sides? Well, it's obvious why they are different for the last line. right? It's clear why they're different for the last line. Because we flipped, right? They used to be the same colors, and now we flipped, so they've got to be opposite. What about every other line? Well, every other piece of line, every other line segment, it used to have different colors on the two sides. But both regions are either inside or both are outside. So they both get flipped. If they were opposite before they got flipped, they are still opposite after they get flipped. Right? It was blue-red, now it becomes red-blue. Equally good. Right? Yeah. Sorry. Okay, which one? Yeah, okay. Let me, yeah, so the question is, what constitutes a proof here? Right? How much detail do you need to give? And the answer is, you know, you won't like the answer. You know, the answer is, at the end of the day, a proof eventually is a social negotiation. Because if you really want to write a proof in full detail, then almost the simplest statement that you need to prove, you'd be writing. Okay, let me say it this way. The analogy is to what language are you going to write your programs in? Are you going to write it in machine language, assembly language, high-level language? You know, are you going to write it in C or Pascal? What are you going to write it in? Well, depends, you know, in what context, right? If you're just sketching out an algorithm, you wouldn't even use any of those languages. You just write it in pseudocode, right? Which is not even a language that's formal, but it's good enough for the purposes, because the person you're speaking to can translate it into an actual program. Right? What matters is that it can be translated into something formal. So when you're writing a proof, it's a negotiation of this kind, where, you know, if you're working on the intricacies of something, you've got to write out all the details. If you're working on something more sophisticated, it's not possible. You know, what you're saying is, look, if you challenge me to, I'll write out all the details, but it'll take me a long time. Right? So I'm going to illustrate this as we go along, and I'll say, well, where in the negotiation are we, and so on. Right? It'll be clear to you where in the negotiation you're. Okay, so proof eventually means that you have a step-by-step procedure, you have a sequence of implications, you know, but the implications may not look exactly like, you know, proposition A implies B, et cetera, you know, in full detail, because if you were to write it out in full detail, it would just take too long. It would be not only would it take too long, it would be too tedious, and it would be hard to understand. Right? You want to write it in a high-level language, and then say, by the way, aren't you confident that if I can actually translate these steps, these are routine, you know, I can do that. Right? That's what the proof ends up being. Yes. Yeah. No. Yeah. Please. Well, it depends upon the context, usually not, but if in the context you're really being asked to prove that, then yeah. Yes? Will the base case always be n equal to 0 is the question. Well, I'm sorry? Yeah, so you know, actually we'll come across examples where you need to extend out the base case. So the base case might be n equal to 0, 1, 2, 3, 4, 5, right? And after that, you can give a general argument. So you know, maybe you can't make the general argument work out until you get to n equal to 5, so you make the base case, you know, n equal to 0 to 5, and then carry on from there, and that's perfectly fine. Yes?
In this case, could we say that the region inside the circular line is a region with k lines?
You could say that, yes, yes. But we didn't use that fact, right? What we did was we just removed this line. We got a map with k lines. We colored it, and then we put this back. Yes. Yeah.
Which part of this proof makes it work for any arbitrary k instead of just k equals 3?
Which part of it made it work for arbitrary k? Oh, good question. So you're asking, when I did this, I drew an example on the board, and I was sort of doing proof by example here, right? And but except that what I was showing you was, what I said was, what I'm appealing to is these general principles. I'm saying, take out one of the lines. Now you have a map with k lines. By the induction hypothesis, no matter what, for k, we know we can color it. So go ahead and color it. Now put back that line. Okay? You have divided this plane into two regions, on one side of the line and on the other side of the line. Go ahead and flip all the colors on the one side. Now we are going to show that this is a proper coloring of the map with k plus 1 lines. And so we say, well, look at every line segment which divides two regions. You look at the regions on the two sides. This line segment is either on the k plus first line, in which case the two regions have opposite colors just by the procedure that we flip one side, or it's one of the original first k line segments, in which case that segment must either be on one side of this k plus first line or on the other, right? And therefore the two regions that are being separated are both on the same side of that k plus first line. And now, because they are both on the same side, they were either both flipped or neither of them was flipped. But if they started off with opposite colors, whether you if you flip both or none, then you still end up with opposite colors. Therefore, every line segment, which the two segments on the two sides of any line segment have opposite colors. Therefore, it's a proper coloring, and therefore that's it. Right. So there's full generality in every step that I carried out here. Does that make sense? Yeah. Yes.
So here you have a closed line.
Yes.
So you have like an inside and an outside. But what would be the inside and outside?
So the question is, well, was I cheating by using a closed curve here? What would happen if it wasn't? What if I had taken out this line instead? What if this was the k plus first line? That's okay, right? Nothing changes. I take this one out, color everything, and then put this one back in and say, take everything on one side of it and flip it. Right? All I care about is there's one side and the other side. And I'll flip one of the two sides. Are we okay? Yes.
In general, if our induction hypothesis is false for some reason, are we going to know? Like, are we going to run into huge problems and try to prove?
Oh yeah, induction is very very tricky, right? Because it's sort of dangerous. Okay, so the question was, what if you end up with what if you end up doing something false in an induction? How bad? Is that maybe what you were saying? Maybe I'm running off with what you're saying, but possibly the thing being said was, well, what if somewhere along the line you have an error in your induction hypothesis and you have something false? Remember, so say you managed to somewhere along the way assume that P of k is, but P of k happens to be false and you didn't notice, or something happened in your proof. As soon as you introduce an error, from then on, false implies anything. Right? So from everything that you chain forward from here is suspect. You can prove anything you want once you assume false. Right? And so since your induction goes on for infinitely many steps, right? It pk, k plus 1, and so on, right? Everything you may have proved might be wrong. So if you make a mistake in an induction proof, it's really dangerous. It's a powerful proof technique, but it's also something that you have to be careful with. Yes. how do you determine the domain? I'm sorry, I'm having trouble hearing you. Okay. So you're asking, how did we formulate this two-color theorem, right? Is that the question? Who came up with this formulation that the line must go from one edge to the other or be closed, right? That's the question? Well, it's just somebody noticed, some clever person came up with this very clever fact, and it's striking, it's very interesting, and because it's so interesting, some of us picked up on it and said, shouldn't we use this to illustrate induction? Okay, that's the story of it. That's all it is. Okay, it's not a it's just something you can. It's just a simple fact that you can illustrate in a very nice way, and it's a very striking example. That's all it is. Yeah. Yes. By the way, this is stretching what this was more for. Obviously, if you really were doing this kind of proofs, you would first build up some machinery to talk about regions in space and so on. That takes some machinery to build up, and that's what I'm skipping here, because that's not the subject of this lecture or of this course. This was just a particularly nice example that I didn't want to pass up just because we don't have that language, and so we are dealing with this at a higher level. So, in some sense, you're not responsible for sort of working through the details of this. This is more to illustrate the point to you. Yeah? Okay. All right, so let's see. Wow, we are moving along. So let me say a few just a couple of announcements. So there are a couple of changes to sections for tomorrow. There are a couple of extra sections that have been added in. There's one from 10 to 11 a.m. in 130 Wheeler and 3 to 4 p.m. in 3108 Echeverry. So you'll find all this information on the website, right? It's going to be updated. Also, one of the 4 to 5 sections, the TA is going to change. So basically what we are doing in this initial part of the class is trying to load balance and trying to figure out which times are most popular and make sure that you have more sections then and move things around, possibly this time and the next. And then we'll be ready for people to sign up for sections. So in the interim, we might request more classrooms so we can add some sections at the most popular time, so we get a nice balanced load. If possible, if campus obliges us with classrooms at those times, but we may have to wait a couple of weeks until that actually happens. Okay. Now, let me also address this whole issue of the wait list. Okay, so as of now, there's roughly 110 students who were on the wait list who've been who've been admitted to the course. I was going to play at the borders and add in a few more students here and there, but then I realized earlier this afternoon that I could actually add in some more students. So it's actually going to be something closer to 20 or 25 more students. I'll try to get that done sometime tonight if I can get to it, or by tomorrow. And at the end of that period, okay, so that's going. This process is going to converge at that point. That's the end of the processing of the wait list. After that, if you still want to take the course, I think it's an outside chance. Maybe you have to bank on other people dropping the course, and you have to. Okay, so the processing, the wait list is not going to be. It has not been processed in this round in wait list order. It's by petition. And if you want to hang on in the course, hoping for somebody to drop, again, it's going to be in that order, right? So what you'll do is you'll indicate to us in some way, by responding to the email that I'll send out. In response, you'll fill out something which says you're still interested in being on the wait list, or you'll renew your petition, and then I'll keep those around in sorted order, and then as people drop, you'll get into the course. Okay, and your guess is probably better than mine in terms of what your chances are of getting in at that stage. I really have no idea. Okay, so just to make sure that there's no confusion, when I'm done with this process, this current process later tonight or tomorrow, I'm going to put up a post on Piazza saying that process is complete, and I've sent out emails to everybody who was admitted saying they're admitted, and everybody who did not get in would get an email saying, sorry, you did not get in. If you wish to stay on a wait list, do X, Y, Z. Okay, so once you see that Piazza post, if you did not receive an email, then you know that there's something wrong, because whether you got in or not, you should receive an email. I should also say for some of you, the email might go into your spam folder because it's being BCC'd to a whole bunch of people. So maybe your spam filter reacts badly to that. Okay, so check. Okay, any questions about logistics? Yes. Well, in this email which I'll send out to those who did not get in, informing them that they did not get in, it'll have instructions of what to do about a second petition.
And that would be tomorrow?
That would be, yeah, ideally it'll happen tomorrow. Yeah? Okay. Yeah.
You said waitlist, like the waitlist petition or waitlist number until there is a new development, so it's just
That's right. Yes. No, it doesn't. Yeah. Yeah. Okay. 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 Okay, so let's talk about another aspect of induction, which is actually quite important, which is that often it matters a great deal how you formulate. Okay, so if you're told what to prove, then that's you're already told prove the following by induction on n. Well, that's straight. Then you're off and running to the races. But in general, you may not know what it is that you need to prove by induction. Okay, and it matters a great deal what statement you actually formulate to prove by induction. So induction is very subtle that way. Sometimes you change the statement a little bit, and it's much easier to prove. Okay? So let's look at examples of that. So just formulations. Formulating I'll just call it formulating induction statement. Right? It's sort of crucial how you formulate it. It makes a great deal of difference to how how easy or hard it is to prove. So here's an example. Okay. That's a chocolate bar. It's a Hershey bar. That happens to be 3 by 5. And you have, 15 kids who are clamoring for pieces of chocolate. And kids, it's you had better be quick in creating these 15 pieces. There are obviously 15 little pieces here. Now, what you can do in order to create these pieces is you pick up any piece of chocolate and you break it along an edge. Right? So you could pick up this chocolate and you could break it like that along this edge, or you could break it along this edge. Okay? Your choice. You just pick up a piece, break it along an edge. Okay? Screaming children. Okay? You're trying to break it as quickly as possible, as few moves as possible. How many moves does it take you? And how should you do it? Yeah, sorry, yes. Oh, can you stack them on top of each other and, as you create pieces? No, it's just one at a time. So, you have a piece in front of you, you pick up any piece you want, you snap it into two, put them down, you pick up one, just keep doing this. Okay? So let's try it, okay. Maybe we want to snap along this one because that's the longest. Then we do this one, that's 2. And now we don't have a choice. We have 1, 2, 3, 4, 5 pieces. We get 5 times 2, which is that what it was? 1, 2, no. 1, 2, 3, 4, 5. Huh?
4 edges.
I'm sorry?
It's 4 times 3.
Oh, 4 times 3. 4 times 3? No, 4 times 2. Sorry, what did I do? Oh, sorry. Oh, you're right. Okay, sorry. Okay, so I split it along these, right? Yeah. Okay, so now I have 3 pieces, and each one I have to split 1, 2, 3, 4. Right. So plus 4 times 3, which is 14. Okay. Oh, 2 is these 2 lines. So first I split this, then I did this. Okay, so now I got 3 pieces, and each of these 3 pieces I had to do 1, 2, 3, 4. Okay, so there were 2 splits and then 3 times 4. Okay, so here's a conjecture. Conjecture is that the minimum number is m times n minus 1. So if it's an m by n, okay, that you can always do it in m times n minus 1, and that's the minimum. That's what it's going to take. Sorry, I just realized I'm going to have to interrupt this for a bit because I didn't tell you about something. So let's go back and talk about one more concept in induction, and then we'll come back to this. Okay? So let's talk about strong induction. Okay, so let's prove the prime number theorem, that every natural number greater than 1 can be written as a product of primes. Now, once we prove this theorem, remember last time we had a statement that we said we'd prove the next time by induction. The statement was n is either prime or has a prime divisor. For all n greater than or equal to 2, n is either prime or has a prime divisor. I'm sorry? Okay. This was something that we wanted to prove the last time. For all n greater than or equal to 2, n is either prime or has a prime divisor. Remember, we used this in what we were doing, in showing that there are infinitely many primes. You see how that theorem implies this? If every number bigger than or equal to 2 can be written as a product of primes, it's either prime itself, it's either a single prime or it's many primes, but in that case it definitely has prime divisors. Okay? So this is our theorem. What we call this is a corollary. It's something that follows easily from the theorem. Right? It's an easy consequence. Okay. So let's go ahead and prove our theorem. Proof by induction on n. Base case n equal to 2. Right? That's the first non-trivial case. And it's obviously correct. Right? 2 is a product of primes. You can write 2 as a product of primes. It's of just one prime, right? 2. Induction hypothesis. Assume it holds for k and step. So k is equal to p1 times p2 times pj. Right? So it's a product of some number of primes. Right? Induction step. We want to say k plus 1 can be written as a product of primes. How do we show that? How are we going to show that k plus 1 can be written as a product of primes? Well, k plus 1 is a number. It's either a prime or it has a divisor. So there are two cases. Case 1, k plus 1 is a prime. Then we are done. Right? It's a product of primes, trivially. Case 2, k plus 1 equal to product of two numbers, m1 times m2. Right? It's either a prime or you can break it into 2. Right? That's by definition. And now what do we do? How do we proceed? Why do we know that this can be written as a product of primes? See, all we know is that k can be written as a product of primes. That doesn't help us say that these can be written as products of primes. So we have to go back to the drawing board again, and we have got to look at what we are doing when we do a proof by induction. Remember what we're doing? We set up our dominoes. There's P0, P1, pk plus 1. And then we said, set it up so that pk knocks over pk plus 1. But that's the way children play with dominoes. Right? Have you ever seen a domino competition where they set up these elaborate patterns where, it's not just one file of dominoes. You have this domino and it knocks over 3 there, and those 3 knock over various ones, and they go over at various rates. Right? It's a much more elaborate kind of domino game. Basically what happens, which one knocks over k plus 1? It's not k, it's something behind it. Right? What you do in this, you assume that by the time you get to k plus 1, all these have fallen. Right? By the time you're about to knock over k plus 1, all of these have already gone. Right? You don't care which of them knocks it over, or maybe it takes a collaboration between this one, and this one to actually knock that one over. That's completely fine. It's still consistent with the game we are playing. That's strong induction. Okay? So it's proof by strong induction on M. Okay? So assume that k equal to p1 times 4. So assume L equal to p1 through pj is of this form for every L less than or equal to k. Okay, so assume the induction hypothesis not just for k, but for everything up to k. You see what I mean? So you're assuming not just that this domino fell, but all of these dominoes fell. Okay, so now we are set up. Now we can move forward, because now we want to prove the case k plus 1. So we say k plus 1 is either prime, in which case we are done, or k plus 1 is a composite. It's a product of m1 times m2, where m1 and m2 are smaller than k plus 1. Right? Where m1 and m2 are both strictly smaller than k plus 1. So they are less than or equal to k, and they are at least 2. Right? They are non-trivial. Neither of these is 1. So we can apply the induction hypothesis to m1 and m2 separately. Right? So because we know from the induction hypothesis, m1 can be written as a product of primes, m2 can be written as a product of primes. So we just multiply it all together, and now k plus 1 can be written as a product of primes. So by hypothesis, m1 can be written as p1, p2 through p sub j. m2 can be written as q1, q2 through q sub. Let me just call this R, let me call this S, just to get two indices that seem related. And okay, so you can write this as a product of some number of primes, this as a product of some number of primes. So when you multiply them, you get a product of some number of primes. That's it. That's the proof. Yes?
What about k? If m1 and m2 are smaller than k plus 1, they have to be at least half of k plus 1. How do you say k base case?
I'm sorry?
What's the base case going to be for this?
The base case is still n equal to 2. That's the smallest number, n, for which we are asserting this statement, for which we are saying something non-trivial. So we still start from the first one. The base case is still the first domino. But then what we are saying is when we go to do the induction step, we are assuming if we want to knock over this domino, we are using the assist of all the other previous dominoes to help knock this one over. Before we were only relying on the previous domino. But now we are saying, by the way, we noticed that when we were about to tip this over, actually all the other dominoes had tipped. So if any of them can assist us, we'll use it. Okay, that's strong induction. Yes?
So what is the thought process behind this? Like, how would I have known that, oh, I need, like, strong induction. I need to write it such that, like, L,
How would you know that? Well, you know, what you would do is either, it depends upon your personality. Okay, so if you like to, you know, there are people who like to feel safe and they like to carry the biggest weapon around with them, then you would always use strong induction because there's no harm in using strong induction. But, you know, another way of doing it is what you would do is you would just try regular induction, and it doesn't work. So then you pull out the big gun and you say, okay, I'm going to use strong induction now. Maybe that'll work. Okay? Yes? Yeah, you're assuming that all of them have fallen. So you're assuming a stronger hypothesis. But it's just a hypothesis you have every right to assume, so you may as well. Yeah? Yes?
I guess it's a question about that. Like, how can we assume that?
What gave you the right to? Well, remember, how did we think of induction? We were sort of working through all the cases. We were saying, look, let's work through examples 0, 1, 2, 3, 4 and prove them, but it's going to take too long. So we said, notice that we can use an assist. The fact that we've solved these already makes it easier to verify that the next one is also true. Okay? But now, we were just making use of the fact that we'd done the previous one. Actually, we started from 0, we worked our way all the way up to 100. Now we know 0 is true, 1 is true, so on, all the way up to 100. Why should we confine ourselves to just assuming that it's true for n equal to 100? Why not assume that it's true for all the way from 0 to 100? Right? That's what we actually did. And so strong induction says, well, we did it. By God, we are going to assume it. Okay, that's right. Yeah.
How would you prove this is simple induction?
Good point. So, in fact, if you want to, if you'd like to, you can prove the principle of strong induction using simple induction. You can actually prove strong, you can formulate strong induction the way we formulated simple induction in terms of P of n, and then you can show that the principle of strong induction follows from the regular principle of induction. Okay, you can actually show it. It's not too hard, but it takes a little bit of thinking. Okay, but then they are actually equivalent. It's just something that it's convenient to think about it this way or that way. Okay, that's all we're doing. Okay. So in the last 5 minutes, let's come back to this Hershey-bar problem. Okay. So can we? Sorry, we just have a few minutes. Can everyone settle down? Okay. Okay. So here's what we're trying to show: that the minimum number of moves, the minimum number of snaps it takes to break down this m by n chocolate bar completely is exactly m times n minus 1. Okay? How would we formulate this? Well, now there are two parameters, not just n. There's m and n. Well, one possibility is we could do a double induction. Actually, let's throw everything at it. Let's do a double strong induction. Or I don't know, maybe call it a strong double induction. Maybe that's what it is. Okay, but it's on two. We have two indices, and we are going to go strong. Okay, so we verify the base. The base case is easy, right? 1 by 1, it's completely clear, right? It takes no moves. Okay, induction hypothesis. So we pick a certain threshold. Right, so we pick a largest size, m. Let's say, let me just call it m naught by n naught. So this is a largest size. Any size which is smaller than this, we assume it requires exactly that many, right? So in other words, if you have an m prime by n prime chocolate bar such that m prime is less than or equal to m naught, and n prime is less than or equal to n naught, then you need exactly m prime times n prime minus 1 of these snaps to break it down. Right? That's the induction hypothesis. Right? It's saying there's some size, we are assuming for everything smaller than this, the hypothesis holds. So we are doing strong induction. There are two parameters that we are inducting on. And now, induction step. Oh my goodness. Oh my goodness. So, oh, I didn't think this through. This is not so easy, is it? Oh, oh. Okay. In which order are we going to go? So we've got to fill the plane, don't we? So okay. Let me see if I can figure. We have only 2 minutes, so let me see if I can think of something quick. Otherwise, there's a okay. So sorry, I was going to do a sequence of these proofs for this, which are, but maybe I'll have to leave it till next time. But okay, so let me tell you the problem that's coming up, right? So what's the next bigger case we want to solve, right? So okay, so what we want to do is we want to go with a bigger one, right? But how much bigger should it be? Obviously, we can't do m naught plus 1, n naught plus 1, because see what happens. You do your first cut, and now you have something of the form. Well, this is small. This is covered. This piece is covered as far as this n goes, but this is too big. We haven't covered this with the induction hypothesis, right? So we want to make sure that we are. Oh, I see. So let's say that in our induction step we are allowed to increase at most one of them, right? Either one of them, and so then eventually we'll get everywhere, right? So let's say we have two induction steps: one where we increase m naught, the other one where we increase n naught. But I guess even that doesn't quite do it. So I think we have to think this through a little bit more carefully about how exactly we do such a double induction and make it work out. But then, okay, so we'll come back and we'll work this through next time and simplify it and so on. Okay. Yeah.